Today we're going to be looking at perfect squares and the square roots of the whole numbers 1 through 20. So when we are finding a square, you must multiply the number by itself. So you're going to take that number to the second power, so an exponent of 2. We call the squares of whole numbers perfect squares. Reminder that a whole number would be 1, 2, 3, 4, etc. So no decimals here. So I'm going to list all of the perfect squares from 1 to 20 here, and I want you to copy them down as we go. So our first one, 1 squared, is just like 1 times 1, so that's just 1. 2 squared is 2 times 2, which is 4. 3 squared, 3 times 3 is 9. 4 squared, 4 times 4 is 16. 5 squared, 5 times 5 is 25. 6 squared, 6 times 6 is 36. 7 squared, 7 times 7 is 49. 8 squared, 8 times 8 is 64. 9 squared, 9 times 9 is 81. 10 squared, 10 times 10 is 100. 11 squared is 11 times 11, which is 121. 12 squared is 12 times 12, which is 144. 13 squared is 13 times 13, which is 169. 14 squared is 14 times 14, which is 196. 15 squared, 15 times 15 is 225. 16 squared is 16 times 16, which is 256. 17 squared is 17 times 17, which is 289. 18 squared is 18 times 18, which is 324. Sorry about the car alarm. 19 squared is 19 times 19, which is 361. And 20 squared is 20 times 20, which is 400. So if you ever forget what any of them are, you just have to take the number and multiply it by itself, and you can figure out what it is, but it is a good idea to have this list memorized. So finding the square of the number means you're multiplying a number by itself. Square root is the opposite of that. So a square root of a number is one of its two equal factors. The word factor means something that you can multiply by something else to get a number. So the factors of 4 are 2 and 2. And since 2 equals 2, the square root of 4 is 2. So to find the square root, you must find a number which multiplies by itself is equal to the number that's under the radical. And that little symbol that you see in parentheses up here and right again here is what is called the radical. So you'll see a number something like this. Like if you have a square root of 4, this is how we would say that. This means square root of 4 is how we would say this. And we think, okay, well, what two numbers multiply by themselves to get 4? So 2 times 2 gets us 4. So that means that the square root of 4 equals 2. So as we move on to the next page, there's some problems to find each square root. So you might want to reference the first page of your notes to help you with this. First problem says the square root of 16. So think about what number multiplies by itself to get 16. Well, we can remember that 4 squared is what is equal to 16. So I could rewrite this as square root of 4 squared, because all I'm changing is that inside number 16, I'm rewriting it as 4 squared. The radical, the square root, and the square are opposite operations, so they cancel each other out. So all we're left with under there is a 4. So the answer, square root of 16 equals 4. Square root of 100 is our next example. We know that 100 is the perfect square of 10, so 10 squared is the same as writing 100 under this radical. But then we know that the square root function and a square are two opposite operations, so they undo each other. That means that all we're left with is a 10, so the square root of 100 equals 10. In our third example, we have the square root of 144, so we rewrite this as 12 squared. And opposite operations, the square root and the square are opposite, so they cancel each other out, and we're left with 12. So the square root of 144 equals 12. So I want you to pause the video and try the rest of these on your own, and then when you're ready to check your work, you can press play. All right, hopefully you took a minute to try these on your own. Make sure you're referencing your list on the front to help you out with these since it's still a new topic. We have the square root of 25 here. The square root of 25 is the same as writing square root of 5 squared. Square root and square are opposite of operations, so we get 5. Square root of 25 is 5. Next problem, we have the square root of 9. 9 can be rewritten as 3 squared. These cancel each other out, and we're just left with 3. In our next example, square root of 49. 49 is 7 squared, so we can rewrite it. Square root and the square are opposites. They go away, and we're left with 7. So the square root of 49 is 7. In this problem, we have the square root of 121. 121 can be rewritten as 11 squared. Square root and square are opposites, so they get canceled out, and we're just left with 11, so the square root of 121 is 11. Number 8, the square root of 196. 196 is the same as 14 squared. The square root and the square cancel each other out, and we're just left with 14, so the square root of 196 is 14. Square root of 81. 9 squared equals 81, so we can rewrite it. Square root and the square are opposite operations, and they are canceling each other out, so we're left with 9. In the bottom row, 256 is the same as 16 squared, so we can rewrite this. The radical and the square cancel each other out, and we're left with 16 is the square root of 256. Square root of 4. 4 equals 2 squared, so we can get rid of the square root and the square, so the square root of 4 is just 2. And in this last example, the square root of 36 can be rewritten as 6 squared. Square root and the square are opposites, so they undo each other, and we are just left with 6. In our next examples, it says find the square of each number. So to find the square of a number, remember you're just taking it to the second power. So 9 squared, that's the same as saying 9 times 9. Exponents mean repeated multiplication, so we're just multiplying 9 by itself twice. 9 times 9 is 81, so 9 squared equals 81. 10 squared, that would be 10 times 10, and that's 100. Go ahead and try the other two, and then check your answers once you pause the video. All right, hopefully you've tried these. 17 squared would be 17 times 17, and that is 289. And our last one here, 6 squared is 6 times 6, and that equals 36. So there's some of our perfect squares listed. In our next example, it says circle the square roots of perfect squares, then evaluate them. So remember, we had our list of perfect squares. That was our whole number that was multiplied by itself to make a perfect square. So we're going to try to recognize these numbers from our original list. So the square root of 32, that's close to some of the ones that we had, but the only ones that are close to that are square root of 25 and the square root of 36. So that's not quite one of our perfect squares. Square root of 64, that is one of our perfect squares. Square root of 324 is also one of our perfect squares. The square root of 101 is super close to one of our perfect squares, but is not quite one of them. Square root of 196 is one of our perfect squares. The square root of 44 is not one of our perfect squares. It's close to 36 and 49, but not quite there. And the square root of 121 is one of our perfect squares. So I want you to pause the video, and I want you to evaluate the square root of each of these 4 problems that I have circled here. All right, so hopefully you tried these on your own. The square root of 64, we have to think what number multiplies by itself to get 64. We could rewrite this as 8 squared. So the square root of 8 squared, since 8 squared is 64, the square root and the square are opposites, so our answer is 8. So the square root of 64 is 8. In our next example, we have the square root of 324. 324 can be rewritten as 18 squared. So we can take the square root of 18 squared. These are opposite operations, so they cancel each other out, and we're just left with 18. And our next one that we had to evaluate, 196, this can be rewritten as 14 squared under our radical. Square root and the square are opposites, so the square root of 196 is 14. And our last one, the square root of 121. 121 is the same as 11 squared. Square root and the square are opposites, and we're left with 11. Okay, in these next examples, the first question says, are these perfect squares? If your answer is no, what perfect squares do they lie between? So 101 is really close to one of our perfect squares, but it's not quite one of them. The closest one to 101 would be 100. The next perfect square on our list is 121. So the square root of 100 and the square root of 121 are the two perfect squares that surround this. That means that if we evaluate this, the square root of 100 equals 10, and the square root of 121 is 11. So this number here is going to be about 10.1, we can estimate. Since it's not exactly 10 squared, it's going to be a little bit more than 100. It's going to be close to about 10.1 as an estimate. The next one we have is the square root of 32. That's not one of our perfect squares. It's close to the square root of 25 and the square root of 36. So it lies between the two of those. The square root of 25, 5 squared is 25, so the square root of 25 is 5, and the square root of 36 is 6. So we could estimate, since 32 is kind of in the middle of 25 and 36, we could estimate that this number is going to be about 5.5, 5.6-ish. And our last one, square root of 121, that looks familiar. That is one of our perfect squares. So we can just evaluate that and say that that number equals 11. So the square root of 21 is 11. There's one of our perfect squares. So down below it says, which perfect square lies between the two perfect squares below? So we had 100 and 144. So think about our whole list. 100 is 10 squared, and 144 is 12 squared. So the one that's going to be in between them is 11 squared, and 11 squared is 121. Try these other two on your own and then press play when you're ready to check. Okay, in number 5 we had 36, which is 6 squared, and we had 64, which is 8 squared. So this perfect square that would be between those is 7 squared, and 7 squared is 49. Number 6, we had we had 49, which is 7 squared, and 81, which is 9 squared. So the perfect square in between them would be 8 squared, and 8 squared is 64. Okay, the last thing that we want to look at for perfect squares are models for these. So it's kind of given in the name, perfect squares, we're going to be looking at squares. And just as a reminder, basic geometry, squares are equal sides, every side is the same. So in this square down here, we have a 10 by 10 square. It's 10 units by 10 units. So the area of this square would be 10 times 10, which is 100. So since there's 10 blocks along this side, and multiply it by the 10 blocks along that side, in this entire square there's going to be 100 blocks because that's its area. So we can say this model is a square. We can see that and we can count the boxes to prove it. Each side is 10 units long, and we know that 10 squared is 10 times 10, or we could rewrite that as 100. So this whole area here, we could say area equals 100 units squared. So we can talk about that area of this square. So looking at these two examples, we want to select the statement that's true about this model. So in the first one, we have a square that's 2 by 2. 2 squared is 4, so we could say that 2 times 2 is 4. We could say that the square root of 4 is 2. We could say that 2 squared equals 4. So those are kind of some of the only true statements that we could say here. So in part A, it said the square root of 4 equals 2. Well, we know that's true, so let's put a check mark next to it. Here, 4 times 2 is 8. That's a true statement, but our model has a square that's 2 by 2. Our side lengths are not 4 by 2, so this is not true about our model, so let's cross it out. Here, we're saying that the square root of 2 equals 1.41. That might be a true statement, but each of our sides was 2, and our area was 4. So we'd be trying to say that 2 squared equals 4. So the square root of 2 is not a correct statement for this model here. Last one we have is 2 divided by 2 equals 1. Well, if we're talking about the area of a square, we want to multiply the lengths, so we're never going to be dividing the lengths. So this is trying to trick you. So your best answer here, it's the only true statement about this model, is the square root of 4 equals 2. And we know that because 2 squared equals 4. So if we wanted to take the square root of 4, we could rewrite it as the square root of 2 squared. Square root and square are canceling each other out because they are opposites, and we get 2 there. So this is true. In our second model, it's a little bit different. We are only given the side length as x. So we want to count, first of all, how long is x. So we have 1, 2, 3, 4, 5, 6 blocks on this side. So we can just say x equals 6 now that we know how long it is. And just to verify, the bottom side and the top side are also 6, so this is a perfect square. So we know some things that we know about 6 for perfect squares. 6 squared is 36. And we also know that the square root of 36 equals 6. So those are some true statements that we already know. Now looking at these, we could say that the square root of 6 equals x. Well, if that's true, if we plug in our x value here, then that would mean that the square root of 6 is 6. But we know that the square root of 36 is 6, so A can't be a true statement. In part B, it says the square root of 36 equals x, and we know that x equals 6. The square root of 36, we already know that that's 6, so that looks like a true statement. If we try the others down here, the square root of x equals 36. If our x is 6, if I say that the square root of 6 equals 36, that doesn't quite make sense because when we're finding the square root of a number, we're looking for two numbers multiplied by themselves to get the number inside the radical. So there is no number that we can multiply by itself to get 6. It's not one of our perfect squares. That's not a true statement. In our last one, we have x squared equals 6. So if I plug in my 6 where the x is and say that that equals 6, 6 squared, we know that that's 36. That doesn't equal 6, so this is not true. So our best choice here would be answer B, the square root of 36 equals x.